Assalamu alaikum, bismillahirrahmanirrahim. I hope all of you are good and fine at your home. Today we will start eighth week lecture number 15 and 16. Before starting on this lecture, we just recall some previous topics and we will solve the last numerical of heat engine or Carnot cycle. So we will revise their formulas. So let's move on. Yes. In the previous lecture, we have learned that efficiency of heat engine could be W net over heat input, and the W net will be heat gained by the system minus heat lost by the system. So the difference of will be W net work output and divided by the total heat input. So we can formulate this formula into the temperature regions. Simplified the formula, we have 1 minus TL over TH, and we have conversion of that TL over TH by this format. We simply divide that, open that W net QH minus 2L, and open the formula of heat input, that is MC delta T, and divide this denominator on both sides. That QH divided by QH, it will be 1, and the QL divided by QH, and the opening that formula. So MCP will be cancelled out, and only the delta T, that is TL and TH, will be remaining. So the formula is derived in this way. The detail formulation and derivation is also available in Sangel book. You can also look that derivation. So move on very quickly towards its numerical. We have example of 6.5 of a Carnot heat engine. It's a very simple numerical. So it's a very simple numerical and example of Sangel book, in which the Carnot heat engine shown in figure 6.48. This is figure 6.48. It's a simple Carnot engine. It receiving the heat amount of 500 kilojoules from high temperature reservoir, and rejects heat to the lower temperature sink at 30 degrees centigrade. We need to determine the thermal efficiency of Carnot engine and the amount of heat rejected to the sink per cycle. So these two parameters need to define. So let's solve this numerical. First we develop the data. Yes. Yes. So we have data. Like we have QH is equal to 500 kilojoules and TH is 652, and TL is 300 degrees centigrade. Remember that it is in the degree centigrade, so we need to, yes, 650 to 30 degrees centigrade, and it is in the degree centigrade. So we have to convert this into Kelvin. So by simple efficiency formula, 1 minus TL over TH, and this is equal to, for conversion of into Kelvin, we have 300, sorry, it is 30. Oh, it is 30. It is 30 degrees centigrade. Yes, it is 30 degrees centigrade. So 30 plus 273 divided by 652 plus 273. So by solving this, we have efficiency of 1 minus sorry, directly solve that, we get the efficiency of 0.67 or 67 percentage. Okay, so we have another formula of efficiency, that is 1 minus QL over QH. We also need to determine the heat loss into the sink QL. So we apply this formula. We just write the efficiency known 0.67 is equal to 1 minus Q. We need to determine QL, and QH is 500 kilojoules. 500 kilojoules. So this will come over here, and 0.67 come over there. So we can make the next page. It will be like QL over 500 is equal to 1 minus 0.67, and it is dividing 500 dividing over here. There on right side it will be multiplied by. So simply 500 multiplied by 1 minus 0.67 is 0.33, and we get the QL 165 kilojoules. 165 kilojoules. So it's a very simple numerical. We solve that. We determine the efficiency and the heat loss into the sink. Yes. Okay. Let's move towards another topic, that is second law of thermodynamic losses statement. We have Planck's statement in previous lecture, two statement of heat engine, the Carnot cycle. We have another statement of Carnot cycle, or second law of thermodynamics, that is a reverse Carnot cycle. In Carnot cycle, we are getting work output by the difference of two temperature. One is the reservoir, heat reservoir, and one is the heat sink. By the difference of these two, we are getting the work output. But in the Clausius statement, we are doing the reverse. That's why we are calling them a reverse Carnot cycle. First of all, we just read out this statement. Then first of all, we read out its statement. It is impossible to construct a device that it operates in a cycle and produce no effect other than transfer of heat from lower temperature body to higher temperature body. Okay, on that case, we have a higher temperature and we have a lower temperature. By the heat transfer from high temperature to low temperature, that is a convection, we get the work output. But in the refrigeration cycle or reverse Carnot cycle, we are doing opposite of it. We are putting work in terms of compressor. We all know that in the split AC or in the fridges, refrigerators, we have a compressor by which we are providing electrical work input to the system, and the hotness is getting from the cold environment and rejecting to the hotter environment. For an example of AC, the room temperature of AC, when it on, it decreases the temperature, and that area is lower temperature. It decreasing the temperature of the room, so it will be the lower temperature space. And whenever any person comes in the room, it extract its heat and reject to the outside of the environment from the outdoor unit. So the flow of energy is from cold region to hotter region. The indoor is cooling device, and it is cooling the inside room temperature, and it takes heat from the room and rejects to the outdoor outside of the room through outdoor. So in that case, we are, and by means of that, we are providing vast amount of energy in the form of electricity, and that electricity utilized by the compressor, and compressor is a working parameter which absorb heat from the cold environment and rejects to the hotter environment. That reflects in the Clausius statement, that it is impossible to operate in cycle that produce no effect other than transfer of heat from lower temperature to higher temperature. Another example which validate this formulation, that transfer of heat from lower temperature region to higher temperature once require a special device called refrigerator. So it not automatically move heat from cold region to hotter region. We need a special device called refrigerator, and refrigerator we have four major parts: compressor, condenser, evaporator, and expansion. We will discuss in the later slide. First of all, we just understand the basic reverse or simplified reverse Carnot cycle. Then we will move towards the actual refrigerators or refrigeration cycle. The Carnot heat engine cycle just described is totally reversible cycle. Therefore, all the processes that comprise it can be reversed, in which case it becomes the Carnot refrigeration cycle. This time cycle remains exactly the same, except the direction of any heat and work interaction are reversed. The cycle is almost the same if you see that, but the direction is opposite. In the Carnot cycle, the heat is flowing from hotter to colder region, and the work is producing in the effect of that, with the loss of some of energy in the environment, of course, like in a heat sink. But in that case, it is totally in opposite direction. The heat is flowing from colder region to hotter region, and in this case we are applying work to the system, not taking work by the system. So the direction is totally opposite, but the cycle is almost the same. Heat in the amount of the QL is absorbed from a lower temperature reservoir. Heat in amount of QH is rejected to a higher temperature reservoir. Work is required to accomplish all these things. So to study the reverse Carnot cycle, we have to differentiate between the Carnot and reverse, so you can easily identify or the difference between the two. So I just compared these two PV diagram of a Carnot cycle and a reverse Carnot cycle, and also write up the difference between between these two cycles. The cycle is almost the same, but in opposite direction. As you see from the PV diagram, that from 1 to 2, 3 to 4, 3 to 4, and 4 to 1, we have a clockwise direction, and in reverse Carnot cycle, the flow or the process will be in the anti-clockwise direction. So you can see, you can compare this to, let's study a single process and compare the single process of Carnot and reverse Carnot cycle. In the Carnot cycle, we have a reversible adiabatic expansion were done by the system, like from 1 to 2. From 1 to 2, the piston is moving towards this direction. Okay, so it is increasing the volume and the piston is moving, so the system is doing work, and the work is done by the system. But in the opposite, in the reverse Carnot cycle, we have a reversible adiabatic compression and the work done on the system. So here we have 4 to 1. You see the difference? From 4 to 1, we have a compression process. We are compressing like this one. We are compressing by the external force of a motor, or the motor is powered by electricity. So motor is pushing the piston towards the bottom of the cylinder, and it is compressing the gas. So it is work done on the system. In 2 to 3, we have isothermal expansion work done by the system. By the isothermal expansion in Carnot cycle, it's still the volume is increasing by the isothermal. And first we have insulation, and then we have a energy loss. So due to that loss, due to the loss of internal energy of the gas is expanding. Okay, and by doing this, we have a work done output. But in the reverse Carnot cycle, from 3 to 4, we have a isothermal compression work done on the system. Again, we have compressing the gas, so that is also a work done on the system. In 3 to 4, we have adiabatic compression work done on the system in Carnot cycle. Yes, in 3 to 4, we have work done on the system. Okay, we are compressing. In that case, we have a work done on the system in Carnot cycle. whereas in the 2 to 3, that is 2 to 3, we have adiabatic expansion burden by the system. So in that case it is burden by the system, the volume is increasing by its own. So in the reverse we have a burden by the system. And from 4 to 1, yes, 4 to 1, we have a isothermal compression burden on the system in Carnot cycle. In reverse Carnot cycle we have isothermal expansion from 1 to 2, yes, from 1 to 2 we have a isothermal expansion burden on the system. So this is the exactly the Carnot cycle, but in the opposite direction. Anyway, I hope you well understand by this. You will also well understand by this by seeing the actual process of a refrigeration and what are the devices which are doing this all the process. The devices which are executing all that processes. So let's learn that devices, and the basic terms and devices are of 4. uh, the first one is the refrigerant. Like in the Rankine cycle, the working fluid is what? Steam. We boil the water to the steam and it goes into the superheated state, and then superheated steam uh, goes to the turbine, and turbine work is produced by the turbine, and then the energy lost by the steam is condensed again into the water, and the water is pumped by the uh, pump, is pressurized by the pump, and the high pressure water goes to the boiler, and the cycle goes on. In the simple way, in refrigeration cycle we have a working fluid called refrigerant. Okay, in the refrigerant we are not using the water or steam or something very familiar gases or gases around our system. We are using special gases as a composition of gases, not only one particular element gas like nitrogen, oxygen. We have a composition of gases in refrigerant, and refrigerant are graded by their special name called R134A. That is available in your fridges, in freezers. R22, R12, R13, that is available on room air conditioner. So we have a different working fluid, and these are graded by the special name of a refrigerant by simple R134A, R134B, R22, R12 as discussed above. So the chemical used for the working fluid is refrigeration cycle. It's called refrigerant. The most special device is compressor, and the compressor is the device increase the pressure of the gas. Like in Carnot cycle, we can use device we can use to extract work out a simple generator. The piston cylinder device run the generator, but in that case we have a uh, reverse cycle. So we are forcing work to the system. So the motor run the piston cylinder device and it compresses the gas. In the latter picture you will understand better way. We have animation of that. This is basically a compressor, and if I play you can understand the working of the compressor. Yeah, it's simply the piston goes towards the top of the cylinder, and the gases is compressed, and when it compresses the lid is open and goes toward the condenser. Okay, I just when we cover all the parameter we will discuss whole video. Yes, heat exchanger, these are devices whose primary responsibility is the transfer of exchange of heat, typically from one fluid to another. It is simple a heat exchanger device. Like in air conditioner we have indoor unit. An indoor unit, if you open that indoor unit you will find that uh, many metal fills is covered with the simple pipe, and in the pipe there is a refrigerant, and the pipe is exchanging heat from the air from the refrigerant to the air. Like you have like in the same way, in that way we have a fins and we have a fan that pushes air towards from the from tube fills towards the outside air. We have two different heat exchanger. One is the indoor unit and one is the outdoor unit. Indoor unit, in the indoor unit we have a chilled refrigerant over here, like the temperature like 5 degree centigrade, and the air, when the air strike with the 5 degree centigrade, it cools down from normal room temperature like 30-32 to 15 to 16-17 degree centigrade. So the air coming from the indoor unit of AC, it's about 18 to 20 degree centigrade. And how it's cooled? It cooled by the refrigerant. So heat exchanger is simple device which exchanging the heat from air, from refrigerant to the air. Okay. We have two heat exchanger. One is in the indoor unit and one is the outdoor unit. In the refrigerator and fridges, we have an indoor coil, and outside you have seen that black coils which exchange heat from outside air. Okay. Entropy is the just like enthalpy is the property, entropy is also a property. It is a measure of molecular randomness. In the process of the process during which the entropy of the system remains constant is called isentropic process, and it is also reverse adiabatic process. So whether it is in the Carnot cycle, we have a reverse, all the processes are reversible cycle. The ideal Carnot cycle is reversible cycle, and it's also reverse Carnot cycle is also reversible cycle, and we have the adiabatic compression expansion in the process of reverse Carnot cycle. So when the entropy is constant, it calls isentropic process. We will see the chart of TS diagram later in the picture. Yes, this is the diagram. So in ideal refrigeration cycle, we have a constant entropy. You see from this process, this is a compression process. We have a straight line, constant entropy, and from again in the expansion process, we have a constant. That's why it is called isentropic process. Okay. The reverse Carnot the refrigeration cycle consists of 4 major parts. One is the compressor that I've shown in the animation. We will also see detail in the later animation video. We have a special device called compressor that compresses the gas, and the compressed gas goes to the condenser. It exchanges heat from outside here from outside here and rejects the heat. Okay. And that pressurized compressor goes into the expansion valve, and expansion valve expand the refrigerant gas, and that refrigerant gas goes into the evaporator. That is in cold environment. Like evaporator is indoor unit and condenser is outdoor unit. For an example of AC, evaporator is indoor unit and condenser is outdoor unit. In the fridges, the inside cooling coil is evaporator and the outside black heated coils is condenser. The process goes on like this. Let's understand the basic refrigeration, how the refrigeration is going on. For an example, I just give an example of practical system. If you have a body spray, you spill out that body spray towards your body, you feel coldness. You all experience the body spray. You just spray over your body, you feel the coldness. A cold liquid is spilled over your body. So when you touch the bottle of body spray, it is not it is on the room temperature. It's not cold, it's not having low temperature. But when the spray when the perfume is going outside of the bottle, you feel coldness. How that process process goes on? It's simply a expansion process. Like when the volume is increased, the temperature is decrease. Okay. So inside the bottle, the volume is very lower. We have a very high. Yes. So I just take this bottle, and it is we have a room temperature. It is also in the room temperature. But when I spill this body spray, my body feels cold liquid. How the liquid becomes having a low temperature when it is in the room temperature? It's just an expansion process. The pressure inside this bottle is greater than outside pressure, outside room atmospheric pressure. So when I just spill out, when the pressure, when it comes to the lower pressure, the volume of the gas inside the the volume of the refrigerant gases increase by going into the larger volume atmosphere. So the temperature cool down. The it's simple, the natural process. So in this way, to so we have seen that to produce low temperature, or to produce refrigeration, to lower the temperature of the air or any environment, we need to have high pressure. For an example of a body spray, the inside pressure of the body spray is higher, and the outside we have ambient atmospheric pressure. So whenever the high pressure goes to the lower pressure, the temperature becomes low. So we need to have flow from high pressure to low pressure, and to increase the pressure we need device called compressor. So now you are understand why we are using the compressor. Compressor is the key device which producing the cooling effect. So to produce a cooling effect, we need to move refrigerant from higher pressure to lower pressure. Okay, later we understand why we are using a special refrigerant beside just water or steam, etc. Okay, so we compresses the refrigerant gases by applying external work through a motor, and the motor is driven through electricity. Okay, so that high pressure goes to the condenser. When the refrigerant compresses, for example like this, when the compressor is compressing the refrigerant, the temperature becomes high. Okay, we don't want to have a high temperature, as we need to have a cooling effect. But when we compresses the gas, it becomes the temperature will increase. Okay, so to lower that temperature of a refrigerant, we send it to the condenser. And what is condenser? From your daily experience, a device called outdoor unit. You see that in the outdoor unit there is a multiple coils, multiple pipes inside, and the pipe is covered with the fins to increase its surface area, so it interact more air and rejects more heat toward in the outside air. Okay, so similarly, the condenser is releasing. So the refrigerant come into the compressor in the normal room temperature like 23-24 degrees centigrade, but when it compresses, the temperature is elevated around 70 to 80 degrees centigrade, and outside temperature we have a normal maximum 30 to 40 degrees centigrade. So that 70 to 80 degrees centigrade refrigerants cool down with the outside air. Okay, and when it's cooled down, you see that the temperature of refrigerant will not decrease, because we have a constant temperature. Okay, I just explained the process with that wet dome. Okay, you understand the phase change process, you also understand the wet dome. Inside the wet dome we have a mixture of gases, and the left side we have a complete liquid, and the right side we have a superheated uh, form. Okay, so the compressor, from this point to this point we have a compression process. So during the compression process the temperature is elevated, like I told that it is depend it ranges from 70 to 80 degrees centigrade. If you touches the outside tube of the outdoor unit, you feel that it is in a high temperature, like 70 to 80 degrees centigrade. Okay, so when the refrigerant goes into the condenser temperature is not decreasing. Okay, you see that the temperature becomes constant in the condenser process, but it rejects the heat into the outside environment. So when it rejects the heat, the phase of the refrigerants become change from gases to liquid. In that point, you see that in this point we already learned the Rankine cycle, and also learned the wet dome and all that things. So you are easily understand when the cycle goes from this point to this point, we have a phase change process. And in the Rankine cycle, we have a opposite direction. We are converting water to the steam, but here we are doing opposite. Okay, the high temperature gas done by the compressor is changing from gases formed into the liquid form. Okay, so after after getting out from the condenser, we have a liquid form, but we have a liquid form, and before condenser we have a gas form, and after condenser we have a liquid form. So in this process, heat is rejects into the outside environment. Okay, now that high pressure, then when we move that high pressure into the lower pressure, the cooling effect is produced. You see that from process for after condenser to the evaporator. This is a condenser to the evaporator process. So when the refrigerant goes from condenser to evaporator, we have a loss of pressure, like in the body spray. We have a high pressure inside the body spray. When it goes out into the lower pressure, it produces a cooling effect. In the same way, when the this high temperature refrigerant, high temperature and high pressure goes to the lower pressure, it produces a cooling effect, and the temperature, you see that line, the temperature becomes down when the process between the process 3 to 4. This is process 3 and this is process 4. So from 3 to 4 the temperature is decrease. Okay, how it possible? Like for an example of body spray, you understand that the inside the cylinder we have high pressure, and outside is the normal atmosphere pressure. So the difference of due to the difference of pressure, we have a cooling effect. But how we are doing this in the air condition or fridges or AC? We need to imagine the the coil of a condenser is about 3 to 4 millimeter. Okay, it has a higher dia, and then we decrease the dia with the capillary tube. Okay, we decrease the dia with the capillary tube, and we shrink the volume. I just show the capillary tube. Okay, yes, we get the image of capillary tubes. You can see in the picture, it is simple a copper pipe, small, very tiny dia of a pipe. So how we perform this capillary or expansion process? We have a liquid after the condenser. We shrink down its the volume. The dia of a condenser is about like 2 to 3 not to, 10 millimeter, is about 8 to 10 millimeter. So we shrink down this dia about 0.5, 0.6, 0.3 millimeter. It's a very small dia pipe. Okay, so when we shrink down the volume, okay, the volume will decrease. Okay, and suddenly in the evaporator we have a larger dia. So in the capillary tube or expansion valve, we have a lower dia, and suddenly we have a higher dia. So when it moves from low volume to high volume, the process the pressure will decrease. Okay, and the result of decrease of pressure, the cooling effect produced. Like for an example, this we have a the liquid, the perfume liquid inside this cylinder, it has a very low volume. Okay, when it goes out towards the atmosphere, it goes towards the higher volume. So due to the higher volume, what just happened, the temperature becomes lower and we have a cooling effect. In the similar way, let's move towards our lecture slide. Okay, in lecture slide, this is the expansion process. We have a capillary tube, it's very small diameter tube, and when the refrigerant moves from very low diameter tube to larger diameter tube, the volume, due to the increase of volume, the pressure decrease in the evaporator, and due to this the temperature becomes lower. And if we talk about the our room air conditioner, room AC, we have a temperature about 5 degrees centigrade, and that 5 degree, when we have a tube of 5 degrees centigrade, it interact with the room temperature like 25, 26, and when the 25, 26 degree of air interact with this 5 degree refrigerant, the temperature of the indoor unit becomes lower. So the air is coming out from the indoor unit have a low temperature, about 17 to 20 degrees centigrade, and it diffuses with the room temperature of 24, 25. It decreases the overall temperature of the room, and up to the set point, if we set the temperature of AC around 23, so the compressor work till the whole temperature of the room becomes 23, and when it reaches the set temperature, the compressor stop. And when the temperature increase again by the human temperature body, we have a body temperature about 37 degrees centigrade. So our body is continuously rejecting the heat into the inside room. So when the temperature of the inside room increase, the compressor start again, and the cooling process goes on. So I hope you understand this process. Let's have an animation so you better understand the whole process of a refrigeration cycle. Okay, yes, this is a compressor. It compresses the gas, and due to the compression, the temperature of gas what increase, and when it goes to the condenser, that 70 to 80 degrees centigrade of refrigerant, the phase change process occur. It not decreasing the temperature of the gas, but it change the phase from gases to liquid. Okay, when the liquid forms comes, and not only this, we don't just have a expansion process from a capillary tube or expansion valve. You just understand that the volume taken by the gas is larger as compared to water. Okay, the gases are taking larger volume. So when we uh, when we change the phase of a gas, the molecules contract, and the molecules contract up to the form of liquid. So you just see that it is not the process of expansion tube, but it also the phase change process that producing a cooling effect. In the condenser, the gases is contracting and changes it from gases to liquid. Okay. Yes. So here we are contracting the volume of a refrigerant into the liquid, and due to this process, it automatically the volume of the refrigerant becomes lower. Okay, and to enhance this process, we have a capillary action. Here we have a capillary action. The liquid refrigerant goes into the small volume of a tube, and when the volume suddenly the volume is increased in the refrigerant, the temperature gets lower. You see that we have a high temperature refrigerant over here, but we have a lower temperature of a refrigerant gas. Okay, we'll just see. Okay, again, in the evaporator process, we have a liquid refrigerant and have a very lower temperature refrigerant. You can see from this, we have a temperature like here 70 to 80 degrees centigrade, but here we have a temperature from like 5 to 10 degrees centigrade. Okay, so again you see that the process is going from this point to this point, and this is saturated liquid point and this is saturated vapor point. So again in the evaporator, it exchanging heat from the inside room and decrease the temperature of inside room, but it does not change the temperature of a refrigerant itself. Again in the evaporator, it changes from liquid to gaseous state. Okay, here you can understand that. Yes, you see that the temperature is not decreasing, but it again the phase is changed from liquid to gases. Again the molecule is expanding and changes its phase from liquid to gas. And after evaporator, we have a gaseous form of refrigerant. Okay, and the compressor suck that gas again, and that compresses it. Okay, so the whole process goes on, and this is the in this way the refrigeration cycle moves. Okay, so in next lecture we will discuss its numerical, its formulation, etc.